This is Stephen Warneberg with my presentation on digital data acquisition for MECH 3020, section 804 for spring of 2021. So to give you a background of digital data acquisition, analog signals are continuous curves which are composed of infinite data points. So recording a true analog signal on a computer would theoretically require infinite storage. A discrete digital representation of an analog signal must then be made for a computer to be able to process and store the data of interest in actuality. So there are many factors that must be considered to correctly perform this operation. The objectives of this laboratory were to learn how to set up a data acquisition board, practice using the data acquisition board to acquire digital data from a variety of analog signals, learn about the three types of digital data acquisition error, and identify and practice implementing the methods for avoiding these errors. So the process of digital data acquisition is that you have a physical process that you want to measure, which could be like position, velocity, acceleration, temperature, or strain, or any other physical process. And you would use a transducer sensor to measure this process. So like an LVDT could measure position, an accelerometer could measure acceleration, a resistive thermal detector or a thermocouple could be used to measure temperature, and a strain gauge could be used to measure strain. So the analog signal from these transducer sensors would then be conditioned. Ways of conditioning a signal would be like using a filter on it or an amplifier. And then this this conditioned signal would then go to the analog to digital converter to be converted to digital, which could then be saved on the computer. The things to be cautious of are the three types of error, which are aliasing, clipping, and quantization error. And sampling parameters and equipment specifications to consider are sampling rate, filters, dynamic range, and number of bits, because these are the things that will either cause or prevent or minimize errors. So aliasing occurs when an insufficient sampling rate is used to convert an analog signal to a digital signal. And alias signals are false signals, which appear because multiple sine waves can intersect at the sampling points. And the alias signal comes from higher frequency signals, but appear as lower frequency sine waves that intersect the actual signal at all sampling points. So as you can see in the figure on the right, the actual signal is like high frequency and blue, but it can be intersected by a lower frequency signal at all points. But this lower frequency signal actually doesn't even exist. It's just at the same, it's at the same amplitude at each point that's being measured. So it can appear to be a signal that's in the range of signals that you might be studying, but it's actually coming from, it's actually just a representation of a much higher frequency signal that you don't want to be paying attention to. So in order to avoid aliasing, you can follow the Riley criteria, which is shown in equation 1, and that is to use a sampling frequency that's greater than twice the frequency of interest. And if you need an accurate amplitude description, you also need to follow recommendation 2, which is to use a sampling frequency that's greater than or equal to 20 times the frequency of interest. And then you always want to use anti-aliasing filters, because that will just filter out the analog signals at a very high frequency that would cause alias signals in the first place. The second type of error is clipping error, which is an error of amplitude description, and it's caused by an insufficient dynamic range. So as you can see in this figure on the right, it's showing an example of clipping error, which is the dynamic range is not sufficient. So the signal that you're measuring is actually exceeding the dynamic range. And in cases like this, the digital signal that you're recording at these points is just the maximum value that you're measuring for. So you're not getting an accurate amplitude description. And the only way to avoid this is to use a sufficient dynamic range that fully encompasses the signal of interest. But you also have to consider that excessively increasing the dynamic range could exacerbate the third type of error, which is quantization error. And quantization error is another type of amplitude description error. And an an analog to digital converter has a limited number of discrete values that it can use to describe an analog signal. The analog to digital converter must round the description of the analog signal to the nearest discrete value. And the number of discrete values that the analog to digital converter can use to describe a signal is correlated to the number of bits used to describe the signal. So in this figure on the right, you can see that the analog signal is very smooth, but the digital signal that we're measuring is very blocky, so it's not accurately describing the analog signal. And this could be minimized by using more fine resolution, which would mean increasing the number of bits. So your digital signal would still be blocky, but the blocks would be much smaller, which would just make the description of the signal much more accurate. So resolution is a measure of how accurately a signal can be described regarding quantization error. Resolution increases directly with the span of the dynamic range, and resolution decreases with 2 to the power of the number of bits used. And these traits are shown in equation 4. The maximum quantization error is plus or minus half the resolution, as shown in equation 5. So in assignment 1 and the first part of assignment 2, we measured 4 signals with 100 hertz, 1 kilohertz, 4 kilohertz, and 8 kilohertz frequencies. And the important sampling parameter to take note of here is that we're using the sampling frequency 4 kilohertz, and we weren't using any filter for these signals. So you can see right off the bat that the sampling frequency that we're using is 40 times greater than signal 1, 4 times greater than signal 2, equal to signal 3, and half that of signal 4. So we can expect signal 3 and 4 off the bat to be alias signals. Signal 1 should be all good to go, and signal 2, because it passes recommendation 1 but does not pass recommendation 2, we would expect to not be alias, but also to not have an accurate amplitude description. And then in the second half of signal 2, we basically, second half of assignment 2, we basically did the same thing that we did in assignment 1 in the first half of assignment 2, but this time we used anti-aliasing filter. So basically what we'll expect is for the results to be very similar to assignment 1 in the first half of assignment 2, except that we should expect DC offset to be removed, and the signal 7 and 8, which both fail the Riley criteria, and recommendation 2 should be attenuated to be basically 0 because they greatly surpass the anti-aliasing filter's cutoff frequency. So as you can see, the results that we got from assignment 1 and 2 are pretty much exactly what we would expect to happen, where signals 1 and 5, which satisfy both recommendations, are not aliased and also have accurate amplitude description, with the only difference between these two being that signal 1 has DC offset and signal 5 does not, because signal 1 was without the anti-aliasing filter and signal 5 was with the filter. And then likewise, signal 2 and signal 6 are very similar to each other, but in this case, they don't satisfy recommendation 2, so they don't have accurate amplitude description. Signals 3 and 4 are alias signals like we expected, which is why they don't even really look like a sine wave. But as you can see with signals 7 and 8 on the right, they're the same frequencies as signal 3 and 4, but this time we're using the anti-aliasing filter, so those signals 7 and 8 are attenuated to be basically 0. In assignment 3, we studied clipping error, and we basically kept the sampling parameters the same as assignment 2. So the important sampling parameter to note here is that we had a dynamic range of 5 volts, and we are studying a 4-volt RMS signal. So using equation 6, we can determine that a 4-volt RMS signal would have a peak voltage of 5.657 volts, and that obviously exceeds the dynamic range of plus or minus 5 volts, which is why in figure 6, you can see that there is clipping error where the peaks on this sine wave appear to be flat, and that's because we're surpassing the dynamic range, so we're just measuring at these peaks, we're just measuring plus or minus 5 volts and not the actual amplitude of the signal that we're trying to measure. So to be able to fix this, we would have to increase the dynamic range. And on our digital acquisition system, that would be bumping it up to plus or minus 10 volts, because that's the next level that we're able to select. So in assignment 4, we were measuring quantization error. And so what we did here was turn the amplitude of the function generator all the way down, and then turn the dynamic range up to 10 volts, plus or minus 10 volts. And then we measured 2 signals, one with 12-bit resolution and one with 16-bit resolution. And using equations 3 through 5, we can easily determine that signal 11, which is measured with the 16-bit resolution, has like over an order of magnitude greater possible values to describe the signal with, compared to signal 10, which used 12-bit resolution. And that also means that the maximum quantization error is like more than a whole order of magnitude less than that of the lower resolution measurements. So the results from this assignment are as we would expect. On the left in figure 7 here, we can see the 12-bit resolution signal looks very blocky, and on the right in figure 8, the 16-bit resolution looks almost perfectly smooth. But it's important to notice that figure 8 is not perfectly smooth. It still has quantization error, but it's just minimized so much because we're using more fine resolution, that it basically is, it's not effective. It's not putting a great impact on our data. So our data is pretty much fine, even though there is still some quantization error, because you're never able to completely get rid of quantization error. So some recommendations that we can take from this lab to correctly perform digital data acquisition is to always use anti-aliasing filters, always follow the Riley criteria, use a sampling frequency that's equal to or greater 20 times the frequency of interest if you need an accurate amplitude description. You want to use a dynamic range that fully encompasses the signal of interest, and you always want to use adequate resolution. And these are just the sources that I use to gather figures and also information to make this presentation.